Okay, so we started with linear
Yeah.
regression. We're
Yes.
looking at,
So as I was saying, so suppose that H is degree 3 polynomial or maybe sine, cosine, something like that.
okay,
And then our like assumption is that H star is linear. So H is a complicated function. H star is linear, but the H star that which was used to generate the data, we don't know that H star. Our estimate of H star is H hat, which will be again linear, but
yeah,
need not be the exact same linear.
will not be the
We are
exact.
trying our best to predict the linear one. And even if like H is equal to H star, H hat may not be H star
Yeah,
because our data is limited and we may not be able to predict the right one. Even if we know which class of models it is coming from, which class of functions, we may not be able to predict. So we do our best guess among all the possible functions. So that is a capital H thing, class of allowable functions. We are assuming that. And within that, we are doing our best guess.
okay.
So which is the best guess is H hat. And the guess is based on some loss function minimizing.
So when we do the sum of least squares, we're
Yes.
we're taking the difference of H and H hat. Is that correct?
No, no, that's not correct. We are difference between Y and H hat.
Oh, why? Why? Because
From
why?
the data.
Because I have to include that. Okay, yeah. Okay.
Yes.
Okay. So it's not just H, it's I have to include
Yes.
that noise then.
You cannot really minimize something that has H star or something or H because you don't know those, but you know the Y.
You know the
So
why.
you can include the Y. So remember that when you are doing the actual data analysis, you can only include things which you know,
Yeah.
and the rest is unknown. You have to estimate.
Yes.
So because you don't know H or H star, we cannot include those, but you do know the Y. So you measure your distance from the Y to H theta.
Okay. Okay. Measure the distance from the Y to the H theta. Yes, because Y is the actual coordinate then. Okay.
Yeah.
And we don't know H and we don't know H star. Okay. And then predict Y equal. But then why does it say this then, Sujay? Y is equal to, oh, that's just a prediction.
That's the prediction.
That's the estimate.
So
Okay.
based on our estimates, if you have to predict the Y value for a new X value, then our prediction will be using that function H hat
Got it.
because that is our best estimate.
Yes. Okay. Okay. Since learning an arbitrary function is intractable, and not a well-posed problem, we assume the function H.
Yes. So we restrict basically our class of functions. That is the capital H. And in linear regression case, the class of functions is all linear functions.
Linear functions. Yes. Yes. And H is the inner product of X and the parameters.
Yeah.
Okay, great. With the class of functions parameterized by a vector theta, problem of learning H reduces to the problem estimating the parameters. Perfect. That's great.
Yes.
And then we estimate the parameters using minimizing the loss. This makes complete sense. I'm
Yes.
okay with this then.
So this setup is very generic. We haven't specified what the loss function is yet. But for least squares, we assume that the loss is you take the difference and then square it.
Yep. Yep. Yeah. So this is generalized for my
Yes.
functions, and then we're dealing with linear. Okay. Here and in the following, we use the hat notation theta hat to indicate that this variable is estimated based on the data. Yes.
Yes.
Okay. Yeah. So honestly, all of this is pretty generalized. This
Yes.
first page is all for regression
Yes.
in general.
Yes. So this is general machine learning,
This is
I would
general
say.
supervised machine learning. Okay. Yes. Okay. Okay. Cool. Then linear regression, we had, so this is class is a set of all linear functions. Okay, so now they've just taken this is H and then this is my noise, right?
Yes.
And it's for each data point, right? I would be
Yes.
the data points in this case, right? So it'll be for
Yes.
each data point. Okay.
And then we convert it into a matrix notation. Y equals X theta hat star plus A.
Cosine. Okay. Wait, I'm sorry. We convert to what? We convert to
The matrix kind of notation.
matrix notation, right? Yes. Okay. So
So
product.
that is for like computational purpose.
Perfect. Okay. Yes. We focus on the linear model where each function passes through the origin for notational simplicity, but in practice, we usually fit a model. Yes. Okay. So this is what he was saying was like the
Yes.
affined
Yeah,
function.
find version of the same thing, which is equivalent to adding a one vector in
One
your
vector.
data in
Yes.
the regressor set.
You'll have a starting point then. Yes. Okay. Features. What does this mean? It includes a constant term.
That's the same thing that you can add the one to accommodate the constant one.
So what is the tilde notation then mean here, Sujay? What is the thing on top?
Oh, so because they added the one, so the earlier theta is not the same as now new theta because
Yeah.
we added another constant term theta naught. So that's why they are using the tilde thing
Okay. So
to
that's why it has to
differentiate. Like it's nothing new. It's just extra notice.
extra initializing term then. Okay.
Yes.
So we can assume that without loss of generality that the linear model passes through the origin,
Yes.
to predict the crop yield of a farm. We have also there's linear relation. To find the parameter theta describes that data well.
Yes.
Okay, so now we have our
We are choosing the loss function, and this is the main list square
yes.
loss function.
Why do I have to do 1 over n again? I forgot about
You don't have to, but when you are expressing the loss, if you don't do the 1 over n, then basically the total loss depends on the sample size, right? So suppose I repeat this exercise for two different training set. One has 1,000 points, another has million points. I want to compare which one I had better fit. Then 1 by n is like more justified there, right?
got it. Got it.
So that's the reason people do 1 by n. There's no other.
Got it. The squares cost function is convenient for a variety of reasons. It can be numerically minimized efficiently as it is convex. Yes. So now we get into convex optimization, right? And it has
Yes.
a bit of geometric probabilistic interpretations. That's fine. So least squares is equal to the minimum of r theta,
Yes.
which we define.
This thing.
Yes. And r theta is this. Perfect. Okay, that makes sense. Great. Can be computed. Let us comment. I suppose that linearly independent, we must have a parameter vector that's such that, and thus describe the independent variable. That's fine. In the linear regression model, this is only possible if there are fewer examples. In linear regression model, this is only possible if there are fewer examples than number of model parameters.
So if you have more number of regressors than you have data points, then if your columns are basically independent, then they will span everything.
Yeah.
So no matter what the data, what the response column is, the Y column, you will be able to like fit it exactly without any error.
Yes. Yes.
So this is typically called overfitting.
Overfit.
Like you have too many regressors. You have too many features being used.
Or not enough data points then. Yeah.
So there are ways to make this work, which is by adding penalty terms and all.
Yes.
So, but the core linear regression model has this problem that if you have more regressors than data points, then typically you will be overfitting.
Overfit. Is usually in the real world, is the solution to get more data points or is it to reduce the number of regressors?
It can be multiple things. You can reduce the number of regressors. Data points not always possible. You can also do something called PCA.
Yeah, we just did PCA. Okay, yeah. Okay, yes.
Yeah, you can do PCA to effectively reduce the number of data points, or you can do some penalized regression kind like reach kind of stuff.
Yeah. Okay, penalized then. Okay. Thus, fitting a linear model without additional assumptions only makes sense in the so-called overdetermined or underparameterized regime. That makes sense. Larger than the number of features. Yeah. So you want a lot of data points more than the number of regressors. Excellent.
Yes.
Okay, structure of the problem. Great. Okay, so now we get into the matrix notification.
Yes.
This implies that the number of training examples n is larger than the number of model parameters d.
Great. Parameters d. Yes.
If x does not have column rank, then the features are linearly dependent. That's what you just said. Okay, perfect.
Yes.
Okay, perfect. I forgot how we derived this, though, Sujay. I know this. I have
Okay,
this
so
memorized, but I
the
forgot.
easiest way to derive is you have that r theta example
Yeah,
expression, right?
yes, I remember.
So that norm square kind of thing. So, norm square can be also written as like if a vector is V, then norm V square is V transpose V.
Yes, yes.
So you have that expression for r theta. So you take the derivative with respect to theta and set to 0.
Ah, okay. And then you'll arrive at,
Yeah, then you get this.
okay, yeah, because of the, okay, so this is linear algebra.
Yes.
So you're pretty much taking the derivative of this, setting it.
Yes. You just take derivative and set to 0.
Got it. Okay. I'm gonna write, what I'm gonna do on that is I'm gonna write down the steps so that I can remember the linear algebra on there too, because
Yes,
sometimes
yes. We did the linear algebra part
it's,
one of the earlier classes. You can refer to those as well
okay, I
in
have
of the
that.
notes. Yeah.
Yeah. Okay. But it's coming from this, take the
Yes.
derivative, set it equal to 0.
Yes.
Okay. Beautiful. And this is one I want to remember. There are at least two proofs of this proposition. Oh,
This is like bringing in the convex optimization theory into this, which is a bit of overkill, but it's good to know as well. So it's a good thing to learn. So this is the definition of a convex function.
yes.
And for any convex function minimization, you can just set the derivative to 0. And whatever solution you find is the global minimum.
Yes.
These
So
are the two things.
what this was saying though, right, is that everything, so if I'm at a previous point,
Yes.
everything has to exist above it, right? That was what it was.
Yes.
All of the value, this value is going to be above
Yes.
value if strictly convex and if only inequality. Okay, perfect. Why is this difference than this? What is the difference here?
Not a
0.
difference. It's just applying the recursion.
It's just applying.
For the special case that the derivative is 0.
Okay. But oh, because then that'll be a global minimizer then, right?
Yes.
When the derivatives
Yes.
equal.
Yes. That's what we are proving, that this is not a
This
local minima, it's a
derivative,
global minima.
got
Yes.
it.
So
That
for
makes
general functions, this is a huge concern that your like any minimizer method, any algorithm that you use in say any Python script or anything might get stuck into a local minima instead of a global minima. But the good thing about convex function is that every local minimum is also a global, so you don't worry about that. So
perfect.
that's all the thing. Like
Perfect.
right now in my work, I am working on a minimization problem, which has this problem. Like it's extremely non-convex. So if you don't start from a good point, you get stuck somewhere which is not good. Like the final minima is not a good answer.
Can you describe the problem, Sujay? I'm kind of curious, like in the real world,
Yeah,
how.
yeah, sure. So what I'm doing is, so we have this financial derivatives and all. So just think of like what would be the some stock market share price of something 1 year from now. And we don't know that exactly, but we have some derivatives being traded around that. So some call option, put options. So basically some contracts are there whose prices are known. Now, based on those prices, we are trying to imply a probability distribution for the stock price that will be there.
Okay.
So anything unknown in probability world, we try to summarize our information into a probability distribution. And now general probability distribution can be very complicated. And this is an example where like I tried with something like a log normal or log normal kind of distribution, and those are not good enough. So we have a slightly more complicated parametric distribution, which like the formulas and all are not very nice. It's very ugly, but there are other ways to represent those things and all that. So then basically the distribution has 5 parameters, and I have some 15-20 data points. So I am fitting those 5 parameters by doing this exact same this minimizer of these squares. But if I start close to the actual solution, then I get good, like I reach there, the actual solution. But if I start very far off, then I don't reach there. I go some wrong direction and I get stuck there. And this is happening because the problem is not convex. So that's why for me it is very important to approximately find where the solution is first, then apply the least force.
Got it.
So there are some heuristic methods. There's some literature I read a little bit on this. And people suggested this is how you do it so that like, you don't get stuck into this problems.
In another class, Sujay, we're learning EM algorithm. This
Yeah,
sounds like
yeah,
because
man.
we're involving the probability then into a lot of this as well too, the optimization.
Yeah, EM is a general class of problem solutions where you have this kind of like EM is more relevant for something like a missing data problem
Yeah, that's what we're doing.
or yeah, things like that. But yes,
Cool. Okay. 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 Got it. So you're working on the position there. Okay, perfect. This all makes sense. I'm actually pretty okay on the convexity. Like, I think the intuition is there. I think the math is just maybe something that I need to review.
yeah, you just have to get accustomed to the notations.
Yeah. And then they've
So
actually,
this is that dot product kind of thing. That norm square thing is broken into dot product with itself. So as we discussed, the norm square is just a dot product of v with v, and then v is x theta minus y. So you expand that and then try to take the derivative.
amazing. Amazing. This is not bad at all then. Yeah, I see exactly what they did.
Yes.
Taking the derivative, setting it equal to
And
zero.
then set to 0, and then take
And
everything to one side and get theta.
cool. Okay, great. That's how the n disappears then too, huh? They're setting it.
Yeah, it doesn't matter actually.
Okay. Linear algebraic proof of the proposition. Looks like they're
So
doing
there is some projection related. So we did this as well, where
SVD.
you decompose the X matrix into U sigma V transpose, and
Right.
then the singular values actually appear in the final expression somehow.
Okay, perfect. I'm gonna write this down as well too, so that I can get
Yes.
the
Yeah, please do it with pen and paper. That helps.
yeah. But it makes sense. I see. Wait, why?
Yes.
So this is broken down because this is from here, right? So X.
Yes. Yes.
No. Okay, perfect. Keeps going, simplifying, decomposition highlights the decomposed terms. The
Yes.
first term cannot be fitted by the linear model, as it is the part that lies outside of the column space X. The second part, does it mean this is the
So
first?
this is that Pythagorean theorem projection kind of idea.
Right. Okay.
So you look at the span of the features and then find the closest point. So drop a perpendicular from your response to the span.
Got it. Cool. Okay. Squares and then simplified down. Okay, perfect. Yeah, V transpose V squared. Okay, great. And then we end up, wait, this proof highlights that the least squares approximation is equal to the orthogonal projection of Y onto the column space of X. So this is like the Pythagorean. Okay, perfect.
Yes.
And what was my original U matrix? What matrix is that?
U is coming from that X decomposed singular value U sigma V transpose.
Oh, it's the breakdown.
So
Okay,
that's the definition.
excellent.
Yes.
This is saying the same thing, right? Oh, collinear. Collinear.
Collinearity problems. So if two vectors are collinear, then there will be problems with this because that X transpose X whole inverse won't exist.
Yeah.
And the corresponding problem in a statistical sense is the model is not identifiable. So two different values of theta will give you same answer. So you don't know which one is better.
Got it. Why are we now suddenly dealing with the noise? What, and here are the entries of Z.
We want to know that the model is unbiased. So on an average, we are we will be targeting the true theta. So expectation of theta hat is theta star. That's what we're trying to put.
Got it.
So
Yeah.
remember that theta hat is based on the data. So we want to know like how much bias you have in your method.
Yes.
So just to contrast this, the ridge regression kind of thing, if you do, that is actually biased. So there the expression of theta hat is not theta
Yeah, because there's the penalty term, right?
because the penalty term. So you are trying to improve the stability of the method by compromising on the bias of it.
Yes. Okay.
So that's like the trade.
Okay, this is fine here, Sujay. We're
Yes.
finding the least squared minus the actual there. And then, wait, where did sigma come from? Sigma, where sigma are the singular
Sigma
value.
are the singular values.
Okay. And expectation is over
So
this.
that is based on the decomposition that we did,
Okay,
that
cool.
U sigma because
Cool. Okay, great. And then they just expanded it. They showed that this is equal to this, which is from above, I think. Yeah, we're subtracting those out. Okay, yeah, we're subtracting those. Okay, perfect. No, we're deriving the same thing. Okay, I think linear regression, I'm good on, buddy. I don't think there's
yes.
many questions
Okay.
here. I think it's just going to be I have to write down the.
Yeah, yeah. Write down the algebra, this particularly with matrices, just to be more comfortable with it.
Okay, it's an open book test, so I can write down all the notes and stuff like that too. So
Oh, nice. So you can carry your class notes as well.
I can carry the class notes as well.
Oh, nice. Will it be mostly like a coding kind of problem, or there will be theoretical proofs and stuff
Oh,
as
that's
well?
the so there's two. Oh, that's a good question. So there's two parts. The first part is going to be in class with just our notes, and we have to do it in class, so we'll have to like derive formulas and everything. Then the second part he's going to give as take home, so we can use the internet or whatever we want for
Okay.
the coding part. He's being a little more lenient about on the coding side.
Okay. Okay. Makes
He
sense.
still wants us to write the code out for it, so
Yes.
he did not in class. So okay.
Yes.
Um,
So this is basically to, like trying to motivate the ridge regression by saying that we derive this expectation of loss square, like the difference square is 1 by n summation of 1 by sigma square, right?
right.
Of these singular values. Now the problem is if one of the singular value is very small, then 1 by sigma square, the corresponding term will be very large.
Yes.
So then the expected error will be large. And this is the case as long as there is one singular value which is small. It's possible that all the other singular values are large. There's only one small singular value that might be a problem. So for example, that can happen that if there are two regressors, two features which are very close to each other, all the others are all different, but there are just two which are close to each other. That will make one singular value close to zero.
Yes, that'll make one singular value close to zero if this term is very large. Yes.
Yes.
Wait, sorry, Sujay, I'm getting a bit confused.
Yes.
What is this? This is my expectation of this is going to be my.
So this is expectation of theta hat minus theta star. Theta star is the true theta, and theta hat is what we estimated from the data. So we want to know the difference between them. And because these are vectors, so that's why we are taking the norm square instead of just squaring.
So what does this mean then? What does this represent?
This means that like the mean square error of your theta estimation.
Mean square error of the theta estimation. Yes, yes, yes. This is not least squares though, because
No,
least
this is not
squares are
least
great.
square. Least square is minimizing the error in the y space.
Yes, that's
This is the mean square error in the theta space.
the mean square error of the theta. Yes. Okay. 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 Very cool, actually. Okay. This makes sense.
Yes.
Okay. Their theta is that. Okay. Specifically, its smallest singular value is close to zero, just like you were saying.
Yes. So that's what matters.
In this case, 1 over theta, 1 over sigma squared is x is large, and therefore the expected
Yes.
error above is large. Okay, good. Are we trying to minimize this though too, right?
No, we're not minimizing this.
We're not minimizing
This
this.
is just what we care about, that this quantity is not very large.
Okay. Okay, got it. In order to avoid this, we add a term penalizing the norm of the coefficient theta. Yes. Okay, so now I have my least squares here plus the penalty term. term penalizing the norm. Oh, that's why this is theta, because you're penalizing the
Yes.
the norm
Large
the norm.
values of theta. Yeah.
Well, you're penalizing the large coefficients. Okay, yes.
Yes.
Enforcing the coefficients theta to be sufficiently small. Incorporating assumptions about the solution in this way that the coefficients should not be too large is called regularization. Okay,
Regularization.
perfect. A least squares penalty combined with L2 norm regularization is called ridge regression. So it's literally just linear regression with a penalty term.
Penalty term. Yes.
Ridge regression estimate is lambda. Yeah, this is the hyperparameter, is a
Yes.
regularization parameter. Note that the ridge regression estimate depends on lambda. Different values of lambda give us different ridge regression estimates. Observe
Yes.
that for
So
lambda.
if you take lambda close to 0, then this is same as the least squares
Oh,
because then the penalty term won't exist anymore.
got it.
And if you take lambda tends to infinity, then basically the least square term doesn't matter anymore because this lambda term will dominate and your estimate will be 0.
Yes. So we choose a small lambda when we want the. I'm sorry, I'm a little confused. Observe that for
It's not about choosing, it's just knowing the limits. What happens if you choose lambda too high or too low? So this is basically saying you should not do that. If you choose lambda too low, then ridge regression is as good as least squares.
yeah, linear
And if you
regression.
choose lambda too high,
Then
then the estimate will be close to 0. So yeah,
yes,
everything
perfect,
will vanish.
beautiful. Okay, ridge regression. Oh yeah, oh yeah. So
Yeah, so
it's
this is the
literally
formula. This is basically same. It's
it's
just
the
there is
same
a plus
as
lambda.
it's the same, and then that you have the lambda. Yeah, it looks complicated, but it's the same thing as linear
Yes.
regression. Okay. Recall that theta x theta lambda is the orthogonal projection of data on the column space. Okay, same thing, same thing, same
Yes.
thing, same thing.
Yes. Except that the formula that we derived for x theta hat, that formula has some extra terms.
This formula does have some extra terms. Can I go back real quick to see the original linear regression one? I think
Yes. You can
this
check
is
what.
this is the main
Yeah, this factor wasn't there. Yes.
x theta, right? X theta,
Yes.
x theta. Where did it go?
Not so far back, I think. Next page. Yeah, somewhere below this.
No.
That's below this. Yeah,
X.
this one. X theta hat is U transpose Y.
Okay.
And what do you have here? So that U transpose Y is appearing in terms of dot product between Y and UI. And then another dot product, another multiplication with the UI is the U transpose, basically. Make sense?
Sure, makes sense. And that this is the full vector. I mean,
Full expression, yeah, if you derive. So
the
basically you have that formula that you have number 4 formula theta hat reach, and you just substitute x equals u sigma v transpose, and then do some algebra. There's like nothing interesting in this. It's just deriving like that.
yes. Okay, linear algebra is a diagonal matrix
Yes.
with this as a
Yes.
consequence. Oh wait, this I think this is from like SVD, it becomes this or something.
Yeah, this is like a beautiful. Yes.
It's just a breakdown, right? Of the
Yes. Yes.
do I need to know
Just
any
a diagonal matrix, you multiply term by term.
term by term? Yeah. This concludes the proof of equation 5. Okay, great. Okay, bias variance is definitely going to be on the test, he said.
Okay.
So this is wait, wasn't it squared? I thought it was squared. What's going
No,
on?
so this is just decomposing the theta hat from ridge.
Theta hat from ridge.
Between the signal and the noise term.
Signal and the noise. Okay. Oh, okay. Excuse me. Okay.
So the first term is the signal part and the second term is the noise part. And on an average expectation of noise, we are assuming to be 0. So if you take expectation on both sides, the second term will vanish, only the first term will remain. And in the first term, if you take lambda to be 0, close to 0, then all those sigma I square by sigma I square plus lambda, those factors will be all 1. So if those are 1, you get V transpose, which is identity. So you reach theta star.
Ah, there's the intuition. Okay, that makes sense. That makes sense. Yes, because then you'll just
But
be,
if
yeah.
lambda is positive, then you're scaling down basically all the factors because you're adding more to the denominator. So you can see that each of those terms, sigma I square by sigma I square plus lambda, denominator is bigger than the numerator.
Yes, I got
So
it.
you're scaling down things and that introduces the bias.
Got it.
So that means larger the lambda, more the bias.
Yep. Larger the lambda, more the. Wait, that didn't make sense. If your lambda is really large, then your denominators are all going to be very large here.
Yes. So this factor is deviating from 1. If the factors are all 1, if lambda is 0, all the factors are 1, and your theta hat becomes theta star.
Yes, that I understood.
So if the factors are less than like 1, so you are shrinking down. So you are deviating from theta star.
Yes.
So if you had like a scalar analogy would be like instead of theta star, you have 0.9 theta star, 0.8 theta star, 0.5 theta star. So you are deviating from theta star and you're shrinking down. You're going towards 0. Okay. So that's the analogy. It's only the vector and matrices one.
Yes. Got it. Okay, that makes sense. And then they're just putting it all together here. The second term is a random, determines the variance of the ridge estimator. So this is pretty much what it's saying from
Yes. If you take expectation, this will go.
expectation of those. Yes. Okay.
And it also saying that like you are increasing the bias by choosing higher lambda, but you're also reducing the variance. So
Okay.
there is a kind of bias variance trade-off. And that's what tells us how to choose the best lambda.
Can you repeat the how do we are using this to choose the best lambda?
Not just that. So that is telling us that the bias is there and bias increases with lambda,
Yeah.
but the variance decreases with lambda.
Yeah.
So in general, there might be some sweet spot in between where the total mean square error, which is bias square plus variance, is minimized.
Got it.
And
Okay.
that you can calculate by maybe in a practical case, you can just calculate that for different values of lambda in your data and then see which one it is minimized.
Okay. Got it.
So this is where we do those cross-validation things, training sample and test sample thing, and see what lambda to be chosen.
Got it. Okay.
So technically, lambda is a hyperparameter. It's not a model parameter. So it's supposed to be chosen independently of the model estimation process.
Yes.
And cross-validation is one method for that. There are other methods like here. We can choose based on singular values and stuff.
Maybe a question here, Sujay, is when would we ever use linear regression instead of ridge regression? Ridge regression always seems better or more accurate. Why would we use?
Not necessarily. Like ridge regression has this bias thing. If you want your model to be unbiased, absolutely, then you would use linear regression. And suppose you know that this collinearity problem, etc., is not there. So all the singular value, etc., the 1 by sigma square, the problem that was discussed earlier, that is not there. Then ridge regression is not required. Linear regression is better.
Yeah. So collinearity is when we turn this switch on.
Yes.
Okay.
Yes.
Okay. Got it. Okay. And then this was our bias variance trade-off images, right?
Yes.
Well, it has high prediction. Yes, so this was our lambda values as we're selecting.
Yes.
So
For
there's,
different lambda, we are calculating the MSE, and you can see that there is some choice of lambda where it is minimized.
yes. I don't know if did we ever do this where do you ever take the like finding the global minimum of this function? Yes, right? That's what we're doing pretty much
Yes. Yes. Yes.
in
That's
order
what
to minimize the MSE then, right? Yeah. Okay, so we started with our linear equation, but now we assume that both the equations are drawn from the same distribution. Obtain a data set. This is saying all the same thing, it looks like. Distributions like C joint distribution determined by the feature. Anything new here?
no, this is basically the same thing.
Yeah.
It's just saying how do you estimate, how do you like know how good our model is working.
Yeah,
So one way to do this by doing this R of H hat, which is taking expectation of H hat minus Y whole square.
got it. This is where we end up with the
Yes.
well, two terms
The
then.
decomposition
The
of bias and
derivation. Okay,
yes.
this is all just the derivation of the formula
Yes.
then. Okay.
Yes. This is the bias variance
I'm just
decomposition.
I'm gonna write all this down so that I have
Yes.
this.
Please write those with pen and paper and
Yeah.
try to get
What is the most important thing out of here? It's probably the top part, right? Is the fact that
uh,
we can write it as
it
this.
is that you basically in the final decomposition you will have three terms. One is bias, one is variance, one is noise.
One is bias, one is variance, one is noise. Yes.
In the final line. So the line just above this is called bias variance decomposition. So there are three terms, right? So the first part is bias. The second is noise. Sorry, second is variance. And the third is noise.
Okay. It says the second is variance. The variance of the method measures the variance of the hypothesis.
Of the hypothesis over the training data.
The third one is also variance.
Yeah, so that's basically the variance for the noise. This
Variance.
is the irreducible part, like the part that is not contained in the model. So there is no chance of improving this using our model.
Good. Okay, buddy. I think this first one is cake. I'm just gonna have to write all this down then.
Okay.
Okay, what time is it? 12:56. Can we do maybe a few more minutes on the next?
Yeah, sure.
It
Yes.
actually goes well together. It's the convex optimization. Let's do a little bit more.
Yeah.
What is the date today? Today's the 15th, and
15th.
you're free. When are you free again?
I'm free on Thursday, Friday, Saturday, Sunday.
Okay, can I text you then? Because I have spring break this week right now.
Okay.
So I'll text you
Yeah,
if
let
you
me
see
know.
which days you're free
Let
then.
me know. I might be able to do Thursday, Friday as well.
Sounds good. Okay. Okay, let's start a few minutes here and then I'll have to get going here today.
Yeah.
Convex op. Oh, I've also asked Dad to send you the money. So 45,000 rupees, I think. So he'll send to you then.
Okay.
Okay, yeah, because there's 10 then. Oh, this one's not too bad. I'm actually
Yeah.
fine. This one's okay. Yeah, I'm good with this. I remember convex
Okay.
optimization
Yeah.
well. The
Okay.
proofs, he said he's not going to ask us like the proof of convex optimization, so at least I don't need to
Okay.
write all of
Yes.
it down. So then, yeah, we have the sets. We cannot pass through
Yes.
their intersections of convex sets are convex. These are all just math proofs then, right?
Yes.
Yeah, subspaces,
Yes.
affine spaces. We have the plus B half spaces, which I don't know.
Yes.
What does that
Half
mean?
space is basically you have a plane and one side of the plane, not the other.
Oh,
So in 2D, it will be draw a straight line and then take only the one of the sides of the straight line. Don't take the others.
okay. How
So
do you?
everything lies on that side of the line.
Oh, okay. Less than or equal to B then. So B is your cutoff point.
Yes.
Convex combination, a set of points is defined as a set of convex that contains all of the convex combinations of its element. This is straightforward. I remember this as well too. Great. Function is strictly convex if the inequality above strict whenever x is not equal to y. What is the kind of reasoning behind? So this is pretty much saying that I have
This is basically saying that the convex function lies above the straight line. If you join the line,
joined them.
yes, the curve lies below the line.
If
So
you
a convex function, think
yeah,
of a parabola.
yeah,
If you join any 2 points on that,
yeah,
the part of the parabola between those two lies below the straight line.
yeah. Okay. Yep. Yeah. That's why this is it's yeah. This is the line. This is the line. This is the area below it then.
Yes.
Okay.
Yes.
Got it. Common examples of convex functions. Okay, yeah, linear, quadratics, parabola, any norm. Oh, the norm function is always convex too. He said that's one to
Yes.
remember. Proposition, any medical. Okay, yeah. So we always have a global minimum in our convex function.
Yes. That's the whole purpose of this.
Yes. Differentiable, perfect. This is where I could set this equal to 0 as well too on the right side. Excellent. It is strictly convex if
Yes.
and only if the inequality holds strictly for that. An important consequence is the following optimality condition. If a differentiable function is, yep, perfect. Excellent. Then x is a global minimizer because we are convex. Okay, good. Computational aspects of optimization algorithms. This we already reviewed. This is least
Yes.
squares. I put it in matrix form, even if we can use computing the closed form solution. What does closed form mean? This keeps coming up.
Closed form means you have a basically a direct formula to calculate. Like we have a formula ready calculate. So
Got it. And in this case, this is the closed form solution then,
yeah,
right?
that is the closed form because we have a formula. You just substitute things, you get that.
Got it. Okay, zeroth order for any first order, second order. Yes. And then we have, so ultimately we are interested in understanding computational complexity. What does this mean? Understanding the computational complexity of convex optimization, the number of flops to obtain epsilon accurate solutions.
Flops is floating point operations, meaning like addition, multiplication, division, and those kind of things. So when you're thinking of computationally, how do I calculate something? You try to measure things in terms of how many steps I need, right? How many, the CPU cycles and stuff. So CPU is measured in the number of hertz.
Okay,
So if you have a laptop, for example, it will be few megahertz or something, two
right.
megahertz or 5 megahertz or something like that. So that means the CPU can do that many cycles. So 2 million cycles in a second.
Oh,
And then there are like the standard CPU architecture says that maybe one addition takes this many cycles, two
oh,
cycles or 4 cycles, one multiplication might take 6 cycles. So these are the total number of addition or multiplication you can do with this CPU in a second. So that's why it is important to look at an algorithm. People, if you want to know how many seconds this will actually take, if you want to do pen and paper calculation of that, you calculate how many addition and multiplication this takes, and then how much time those will take, each
uh,
addition and multiplication for your CPU, whatever laptop you use or computer you use.
uh,
So that's like how computers are. And then people might be using different computer specs, right?
yeah.
So instead of comparing between seconds, because your laptop might be much better than mine, so if you compute something and I compute something, it might be that the algorithms are same, but your computer is faster.
Right.
So it's better to compare the algorithm directly in terms of flops instead of number of seconds.
That's what flops means.
That's why, like, if you are like comparing, yeah. So the flops is floating point operations.
Floating point operations. Okay. Is
But
that the
because
same thing as the big O notation? We were learning the big O.
no, big O is a different thing.
Oh, big O.
So floating point is basically how many addition and multiplications of decimal numbers you do.
Got it. Okay.
Integers are faster, but decimals are the basically the standard values.
That makes sense. The
Because
floating.
typically your data will be decimals, right? Not integers.
Okay, and then gradient descent. This one was not bad at all. We've done this in
Yes.
multiple classes, so I am
Yes.
I'm very good with gradient descent.
Okay, good.
Where did we get this from? The up to here, this all makes sense,
Yes.
but
So this is deriving how the error changes in the gradient descent method from one step to another,
okay,
assuming that the true function is quadratic.
function. Okay, got it. So this is so n. This is iteration. Wait, what is the n here?
Yeah, n is the number of iterations you need to do.
That's what I'm figuring. Okay, got it.
So basically, you're trying to estimate that given the inputs, how many number of iterations you need.
Perfect. Very nice. Okay. Okay, buddy, let's pause here then. So I'm glad we got two presentations done. I have
Okay.
logistic,
Yes.
SVM, decision trees, and clustering.
Decision trees. Yes.
I have
Oh, you
four.
have done clustering as well?
Clustering is on the test. Yeah.
Oh, okay. When is the test?
Let's check. Let me check. The test is on in-class written exam is on March 24th.
Okay, so you don't have a lot of time.
Don't have a lot of time.
So you have only basically 1 weekend.
One weekend, yes.
Okay.
March 24th. Okay. I'm gonna keep studying though, Sajay, so I'll be prepared this week. I have spring break right now, so I have time to study and stuff. So
Okay. Sure.
okay, and then I'll check with you Tuesday. I'll make sure that the money has gone through and I'll check to see which dates you're free for Thursday, Friday, Saturday, Sunday then.
Okay.
Okay,
Sure.
sounds good.
Okay.
Okay,
Thanks.
yeah, bye-bye.